This is the third part of this video lecture. In the first part, we saw the statement of a lemma, which says that sections of the function that assigns the measure of a section at a certain point x as measurable function of x. And then from that, we saw a theorem which asserts existence and uniqueness of a product of sigma finite measures, and just by specifying what the product should be on rectangles. And we stated that already. In the second part of the video lecture, that was very long, we were proving the lemma, okay, the lemma that asserts that this function that assigns to each x the measure of the section at x, that this is measurable. And now in this third part of the video lecture, we're going to show the proof of this theorem, the theorem of existence and uniqueness of a product measure. We start from uniqueness. Okay? The uniqueness of this measure, we assume there exists a measure. Okay? We denote it by this funny product here, this notation, but it's a measure on omega 1 Cartesian omega 2 with respect to the sigma algebra F1 product F2. So assume there exists a measure that to each rectangle gives as the product of the sides of that rectangle. Then if there is such a measure, why is it unique? Well, it will be unique by something that we already saw in the proof of the previous lemma. It's because the set of rectangles is a pi system. This pi system generates the whole sigma algebra, and if both measures are sigma finite, then this product will be sigma finite as well. And how can we say that? Well, mu being sigma finite means there exists a n which increase to omega 1, and mu of a n is finite for each n. So there exists this sequence. And nu being sigma finite means that there exists a sequence Bn that increases to omega 2, such that for all n, mu of Bn is also finite. Now, how do we show that every measure with, let's go back here, every measure with this property here, every measure with this property is also sigma finite? Well, we just need to provide a sequence Dn that increases to the Cartesian product omega 1, omega 2, such that this measure mu cross nu of Dn is finite for every n. Well, we need to provide such a set. Well, it's very suggestive. We don't have much of a choice here with what we know. How can we construct explicit this sequence Dn just with what we have? Well, of course, we just take Dn to be a rectangle given by An cross Bn. So this will check the assumption that this measure, any measure satisfying this property here, is sigma finite, and therefore we can use the theorem from week 2, from the beginning of week 2, that says this measure is then unique. Okay. And because it is unique, okay, we just need to get existence. And once we get existence, if we get existence in two different ways, we get already for free that these two ways are giving the same measure, because we already have uniqueness. So the second part of the theorem, let me go back one more time, the second part of the theorem, we don't need to show all the equalities. We do not need to show this equality here. And why is that? Well, that's because if we show that this measure, this here is something that depends on E. Okay? This is a number. This is a number, this number depends on E. Okay. And if we show that this number that depends on E is a measure and that it satisfies these properties, it means we get existence already. And if we can show the same thing about this function here, then we already get existence, but we already had existence and we had uniqueness. But from uniqueness, we get that these two functions are the same. And they are the same, and we denote them by this product, with the extra useful feature that it tells us is explicitly how to compute the measure of a set E on the product space. So if let us zoom in here and be more explicit, what is this saying? It is saying if we have a set like this on the product space, then it's possible to assign a measure to this set, just knowing, if we just know how to measure things down here on omega 1 and up here on omega 2. And we can compute that measure in two different ways. Either for each x, we take this height here and add it, or for each y, we measure this height, this width here, and add it. So we can choose which variable to use to integrate and which variable to use to make measurements. So this is what this two possible integrals to compute the measure here are saying. This one says we can compute it like this and add, and this one says we can compute it like this and add. And both will give the same number, and that number we denote by the product measure on E. Okay, this is just to say, to get existence and the second formula, it's just enough to show that each of those integrals will yield a measure. Okay, what do you mean yield a measure? Well, those integrals start by assuming we have some set E. And we do things with this set, and in the end we get a number. What we have to show is that this process of assigning numbers to sets, it has the properties that are required for us to say it is a measure. This is all we need. And after that, of course, we want to show that when E is of the form A Cartesian B, where A is in the first sigma algebra and B is in the second sigma algebra, then this number is actually equal to mu of A, mu of B. So these are the two things we have to show. First, this thing, and second, that this function gives a number to measurable sets is a measure.